Hello, in this lecture, I'll be talking about photoelectric effect. In the previous lecture, we had discussed something called black body radiation and ultraviolet catastrophe, and how quantum theory could solve the problem of ultraviolet catastrophe and explain the shape of black body spectrum. Photoelectric effect is yet another phenomena where the classical theory fails and we need the quantum theory to explain the phenomena of photoelectric effect completely. It was during his experiments on electromagnetic waves that Hertz noticed that some sparks were flying in the air gap of his transmitter when ultraviolet radiation was incident on one of the metal balls. He was not much interested in this observation because he was doing some other experiment, but others who pursued this observation found out that when light of sufficient frequency fell on metal balls, electrons were ejected from the metal surface. This phenomenon is called photoelectric effect, and the emitted electrons are called photoelectrons. And in the experimental setup that was used to study photoelectric effect, there is an evacuated tube which contains two electrodes, and these electrodes are connected to a source of variable voltage, and the metal plate or the anode is irradiated with light. And the observation is that some photoelectrons emerge from the surface of the anode and they have sufficiently enough energy to reach the cathode, even though the cathode has negative polarity. That is, overcoming the repulsion that is offered by the cathode, negatively charged electrons starting from the anode reach the cathode and a current is measured in the circuit. And it was also observed that slower photoelectrons are repelled before they get to the cathode. And when you increase the voltage to a particular value, say V0, we observe that no photoelectrons are capable of arriving at the cathode and photocurrent drops to 0. And this voltage where no photocurrent is observed, this is called the extinction voltage, and extinction voltage corresponds to maximum photoelectron kinetic energy. As we see the experimental setup, you will understand more about photoelectric effect. This is our experimental setup. You can see that light is falling on the anode and electrons ejected from the anode are trying to reach the cathode in overcoming the repulsion that is offered by the cathode. Electrons which have sufficient energy to overcome this repulsion will reach the cathode and a current will flow in the circuit, which is measured by the ammeter readings. And electrons which do not have sufficient energy to overcome this repulsion will not reach the cathode. And when voltage is this is a variable source, and when voltage is increased to a particular value, we see that the repulsive force offered by the cathode is so strong that electrons don't have the enough kinetic energy to reach this location, and therefore no current is observed in the circuit, and that is called the extinction voltage. Photoelectric effect is not a very surprising observation, but three experimental findings couldn't be easily explained with classical theory. Let us go through what those observations are. Photoelectric effect is an instantaneous phenomenon. That is, when light falls on the anode, immediately electrons are ejected from the surface of the anode. Now, if we are trying to explain it using the classical theory, where we imagine the energy of light to be concentrated, to be spread over the wave fronts. And if we consider that is the case, and if we assume that light waves are falling on the anode, and the atoms in the anode acquire energy from the wave fronts, if we are imagining such a picture, the problem with this picture is the energy is so distributed, and to eject electrons from atoms, you require energies of the order of electron volt. But when energy is distributed in wave fronts, each atom acquires only something like 10 raised to minus 25 watt. So just assume if we are to obtain sufficient energy to eject electrons out of this surface, it would take a lot of time. But here the observation, so there will be a delay between light falling and ejection of electrons if we are assuming energy is spread over the wave front. But here our observation is that it is an instantaneous phenomena. That is, light falling and ejection of electrons happens almost simultaneously. So this observation cannot be explained using our EM theory. Now the second observation is given here in this graph. A brighter light yields more photoelectrons than a dim light of the same frequency. So here we are using the same frequency radiation, except for the fact that we are changing the brightness of the light that is incident on the anode. And we see that for a dim light, if current is I, then for a brighter light, we see the current shooting to 2I. For more brighter case, we see that current is becoming 3 times the initial value. So when we are increasing the brightness of light, we see that more and more number of photoelectrons are being produced, and that is reflected as the increase in photo current. But EM theory suggests that brightness of light, or when light is more intense, the energy of electrons should also increase. But here we are not seeing any such observation. Here the frequency is remaining constant. Frequency is remaining constant means the energy of radiation is of course the same, only the brightness differs. So with increase in brightness, the photocurrent also increases. That is our observation, which cannot be explained using electromagnetic theory of light, which predicts that when intensity of light is more, the energy of electrons should increase. But here we are seeing that it is the number of electrons that is increasing, not the energy. The third observation is that when frequency of light is high, the energy acquired by photoelectrons is also high. So we have plotted a graph here with light of 3 different frequencies falling on the anode, and frequencies are related like this. Nu1 is the greatest, Nu2 slightly lesser than Nu1, and Nu3 is lesser than both Nu1 and Nu2. So we have light of 3 different frequencies falling on the anode, and we see that the photocurrent is pretty much the same, but it is the kinetic energy that is acquired by the electron that differs. So light of more energy gives more energy to the photoelectron. So more is the retarding potential. This explanation cannot be explained by electromagnetic theory of light. So this observation suggests blue light would produce faster photoelectrons than green light or red light. Okay. Now, how this was explained using quantum theory of light. Earlier in the black body radiation case, Planck had proposed quantization of energy in the case of light, He said that energy was concentrated in certain packets called photons, and each photon has the same quanta of energy h nu. So the three experimental observations connected to photoelectric effect can be explained directly from Einstein's hypothesis like this. Here, according to quantum theory, energy of light is concentrated in small packets called photons. Each photon carries the same energy. Since energy is not distributed over all wavefronts and it is concentrated in packets, we can assume that when light falls and sufficient number of packets of energy are absorbed by the anode, instantaneously electrons are ejected. So there is no delay between arrival of light and ejection of photoelectrons. Now the second observation is that since all photons of frequency nu have the same energy, as the intensity of light increases, there will be only a change in the number of photoelectrons but not their energies. So when intensity of light increases, it just means more number of photons are incident on the anode per unit area, per unit time. So more number of electrons get sufficient energy and get ejected from the anode. So when more number of photons are incident, more number of electrons are ejected. The third observation is that higher the frequency, greater the photon energy. Because photon energy is given by h nu, and when nu is large, then h nu is also large. So higher the frequency, greater will be the photon energy. And when photon energy is large, what happens? If electrons require only say 10 electron volt to be emitted, and if they get say 12 electron volt, they will absorb the 10 electron volt and get out of the material, and the rest 2 electron volt they will uh, absorb, and they will move with that particular kinetic energy. So that's the case. So higher the frequency of light incident, the more energy the photoelectrons acquire. Now there is a particular frequency nu 0 below which no photoelectrons are emitted, and this minimum energy that is required for an electron to escape from a particular metal surface, that is called work function. If we are not imposing such a restriction, we would just be seeing electrons pouring out of the metal surface all the time. But that is not happening. We are not observing current every time. Only when light of sufficient frequency is incident on this material, we observe photoelectrons and a current in the circuit. So there is a minimum frequency that is required for the incident light to produce photoelectrons, and that minimum energy is called work function of the metal. It is a characteristic of the metal that you are choosing here as the anode, and work function can be given by h nu 0. So greater the work function of the metal, more energy is needed for an electron to leave its surface. So higher will be the critical frequency for photoelectric emission to occur. Okay. So in the next table, we can see the work function values for various metals. You can see that it is a characteristic of the metal that is being used. And in the list, we see that platinum tops in the work function values. So according to Einstein, photoelectric effect in a given material should satisfy this equation. H nu gives the incident photon energy. Phi is the work function, which is the minimum amount of energy that is required to eject an electron, to bring an electron to the surface of the material, for an electron to just leave the metal. This is the minimum amount of energy required, and rest of the energy is used by the electron as its kinetic energy. So you have a picture here. If light with energy equal to the work function falls on the material, if light of energy equal to the work function falls on the material, it just implies that kinetic energy should be zero, isn't it? Because this energy is taken by the electron to just come out of the metal. It doesn't have any extra energy to travel forward. But when light of energy more than the work function is incident on this material, whatever is the work function, that is utilized by the electron to come to the surface, and the remaining energy is going as its kinetic energy. Okay, so this is all what photoelectric effect is about, and here you can see uh, some calculations for your curiosity. Thank you.